All right, welcome to the first video from chapter 4. So here we're going to do harder problems with Newton's laws in this chapter. This first video first just goes over Hooke's law and springs. So the spring force, because we'll need that for some of these later problems. Now your book actually introduces this earlier in chapter 3, and we sort of glossed over it, but we'll do it in more detail now. And then even more detail towards the end of the course. So we just need to know some basics about springs to be able to use the concept as we deal with energy and momentum problems and all of that in the next couple chapters. Okay, so the problem we want to be able to answer, just a couple, just relating some facts about springs. So here we have a mass on a spring. What's the force on the mass, and then how much time does it take for it to come to rest? So part B requires understanding the motion a little bit, which we'll talk about in this video. Okay, so I drew a picture here in advance because I couldn't trust myself to do this in real time. So this first picture up here, this just shows a spring. So the spring isn't attached to anything, it's not doing anything. This is what its natural length would be. And notice I oriented it horizontally so that gravity doesn't play a role in anything we might connect to the spring. So we'll have a frictionless surface and we'll be putting a mass on it like this. So because that spring, you can imagine, wasn't doing anything before, and even if it's connected to a mass, the ground is supporting the mass. The mass isn't changing the length of the string of this spring or anything. So there's no force on the mass right here. No force on M. So this is understood that I'm just talking about from the spring. There's no force. So I'm going to ignore the normal force and the gravitational force here. So when I say no force, obviously those are still going on, but those will cancel out as long as the motion, our surface is just horizontal here. So what happens if I stretch the spring a little bit? So I grab the mass and I pull it so that it's right here. So the left end of the mass is now displaced a little bit. So from personal experience, you probably know that if you stretch something, if you have a spring and you stretch it, it's going to want to go back to its equilibrium position. It's going to pull inwards on it. Right? So the spring is tugging right here to the right, and it's tugging right here to the left. Right. And another fact that you're probably familiar with is the more that you stretch it, the more it's going to pull back. So in this case over here, in this third case, if you stretch it more, it's going to pull more. So we'll be able to explore why this is a little bit later, but the force is actually proportional to how far you pull away that mass. So if in this third case I pull it twice as far as in case 2, so twice the distance means twice the force. Okay, and this law is known as Hooke's law. So Hooke's law gives the spring force, the force on a mass connected to a spring. So the force from a spring so you might just see this F sub S for spring. So the force by the spring on the mass is proportional to how far away you have it. So I'm gonna leave a little bit of space right here, and then put an X. So I have in mind that this is X equals 0 right here, the equilibrium length of the spring. You don't have to call that X equals 0. You could call that X equilibrium, X EQ, in which case this would be whatever the X is relative to the equilibrium position. So you might see, instead of X, you might see X minus X equilibrium. So that's just allowing for that X position to not be 0 where the spring is at rest. So we're going to put a couple of constants in front of this X though. So one thing is that not all springs are exactly the same. Some springs are stiffer than others. And so there's actually a constant here which is related to how stiff the spring is. So the larger the value of K, the stiffer the spring. So in other words, I could have a few different springs and stretch them all by an amount 1 centimeter away from their relaxed positions. Some of them are going to be a lot stiffer than others. So the stiffer ones are going to have a much bigger force for that 1 centimeter than other ones. You know, if you have a very loose spring and you stretch it 1 centimeter, maybe it doesn't tug very much. That has a low value of K for that spring. Another reason you kind of anticipate that you need some other constant here is the dimensions don't work out. So if you have like a force right here and a length right here, obviously you need something else with dimensions to modify one or the other. Okay, so F is Kx, but we also include a minus sign right here. So what that signifies is that whatever your x direction is, so I labeled it in this figure, the x direction is positive. If you stretch the spring, so in other words, if the mass is at a positive x coordinate, the force is going to be in the negative x direction. But this also works both ways. So if you connect a spring, maybe I should draw this down here. So if the equilibrium position were here and we compress the spring and put the mass here, then we're at a negative x position. So this is negative x, but then the force will be in the positive direction, positive force. So if you're at a negative x position, the force is positive. If you're at a positive x position, the force is negative. So they're always opposite in sign. So the force is in the direction opposite the displacement. Okay. So this works regardless of what you call the x direction, right? We could have called the x direction this way, to the left. But the convention is that we call the positive x direction the direction where the spring is stretching. Right? So that actually wouldn't affect the formula, but that's just the convention here. Okay, so Hooke's law is the force on a mass by the spring. From Newton's third law, you also know that this is the force on the spring from the mass. But a lot of times we don't really care about the spring. I mean, even though if the spring, so in this situation, if the spring is pulling on the mass to the left, then the mass is pulling on the spring to the right, but then the wall is also pulling on the spring right here. So because we're not really analyzing that force or anything, we don't really care about the spring. So most of the time we're just focusing on whatever the spring is connected to. You might wonder why we're so obsessed about springs, and right now it's maybe not quite so obvious, but this formula pops up anytime you have some sort of equilibrium situation. So notice how the spring was relaxed; it was in some stable equilibrium spot. And if you displace the mass from equilibrium, it's just trying to get back to where it was. So you move the mass to the right, it's going to go back to the left. It's going to feel force back to the left. This pops up in nature in a bunch of different scenarios that don't actually involve springs. So for example, you have two atoms. Maybe the bond length is some amount that they like being this distance away from each other. If you pull them apart a little bit, they're going to feel a force of attraction. And if you compress them a little bit, they're going to feel a force of repulsion. So they act a lot like springs, and actually the force is proportional to the distance from equilibrium. Right? So this formula is really, really general, and it's a consequence of basically just being able to approximate the bottom of your potential energy curve with a parabola. So we'll talk about this in more detail when we talk about energy. But basically, if you have, imagine you have a hill, just any shape of any hill. You can take the bottom and approximate it with a parabola, and it's a good approximation. And the fact that the hill looks like a parabola is related to the force being linear. So again, we'll do that in more detail later. But I guess for now, just know that this formula can be used for more general settings other than just springs. It goes by Hooke's law. Okay, so your book alluded to this in chapter 3, but it goes into more detail in chapter 4. If you have this situation where the net force is from Hooke's law, so if your net force, so notice before we were only talking about the force from the spring on the mass. There could have been other forces. But if we say that the net force is the spring force, so if the net force is the spring force on the mass, then we can do a little bit more with this by combining it with Newton's second law. So if the net force is the spring force, then ma, remember the net force is ma, is minus kx. Right, so anytime you have the net force, you can set it equal to ma by Newton's second law. The acceleration is two derivatives of the position. Okay, so the position is a function of time. So you have to imagine x as just not some number, not just a variable, but actually a whole function, a function of time. And so this equation is telling us a lot. It's telling us not just for one moment in time how these two things are related, how ma and kx are related, but for all times in the future. So this becomes so maybe just moving the m over to the other side. So two derivatives of a function is equal to minus a constant. K over m is just another constant. So k over m is positive. With this minus sign in front, this is a negative constant, times your original function again. All right, so this is a differential equation that we have to solve. We want to solve this differential equation to find x as a function of time. So what that'll tell us is the motion of the mass for all times. Right? So if we just focused on this picture right here, so this third picture right here, there's a force to the left, and we could set it equal to ma to find the initial acceleration. Right? So that would be fine for that one moment. And the mass, if we released it from rest, it's going to start moving to the left. But then a short moment later, you're going to have another acceleration, and the mass will be moving. So you'll want to analyze it at some new position. And then maybe at equilibrium, you'll have to analyze it there. So what this equation is doing is it's saying, well, rather than do it separately every single time, why don't we just leave x as a function of time? And then if we can solve this differential equation, then we know where that mass is going to be for all times in the future. That's what's nice about this equation. It'll do all that work for us, so we don't have to keep doing f equals ma over and over and over again. Now your book basically says we solve this by guessing, and it sounds silly. It sounds like we don't know what we're doing, but it's true. I mean, this is, I don't know, if you've taken a class in differential equations, you build up what seems like a formalism, but it's just you have the hindsight of hundreds of years of people's guesses, and you know which ones work out. So they've cataloged all of them into a class called Math 20D. But really, it's you've seen this before. You want a function so that when you take two derivatives, you get negative the function back, maybe with some extra constants involved as well. But two derivatives of a function is the function again, with a minus sign. So the solution, don't let that go. The solution to this, solutions, x as a function of time is, so you could have cosines or sines. So maybe a constant times cosine. So the constant, we'll just call a for now. I'm gonna leave there's a constant in here that I'm gonna leave blank for now. You could also have sines. Right? Whether you have cosine or sine, when you take two derivatives, you get minus that function again. So cosine, a derivative is minus sine, another derivative is minus cosine. So you get minus the original thing back again. For sine, if you take a derivative, you get cosine. You take another derivative, you get minus sine. So both of these work. So a second order differential equation has two solutions. These are our two solutions. You'll notice your book doesn't talk about both of the solutions. They just say, well, one answer is cosine. Now the reason they ignore this And we're gonna talk in more detail about this problem later on in the course. But we can ignore the solution because of our initial conditions. Okay, so notice when you plug in t equals 0, when t equals 0, cosine of 0 is 1. Okay, so which solution you use depends on your initial condition. Okay, so if you stretch the mass and then you let it go and you call that t equals 0, then the mass is at its farthest possible spot. This is going to be x equals a. Right, notice how x and a have the same dimensions right here. Cosine is dimensionless. So this a, this constant a in front of the cosine, is a distance. It's a position. Okay, and because cosine is from -1 to 1, it's actually the maximum position, maximum distance away from equilibrium. So cosine is the function that when you plug in t equals 0, you get cosine is 1. And so cosine is the one we want for this particular situation. If we call t equals 0 where we stretch out the mass and we let it go. So if the mass is stretched out the farthest possible at the x equals a, then we're going to use the cosine. Suppose we let go of the mass, and then the moment that the mass passed the equilibrium position, either moving to the left or to the right, we would use a plus or a minus. So b could be positive or negative. We would use a sign. Okay, so we're not going to use the sign because of our initial condition. We like this. If our setup has the mass at x equals a when t equals 0. Okay? So again, we'll do this in more detail later. You can write it, in general, you have to add, you know, both of these two things could be there. Or you could have cosine of something times t plus another constant. So instead of cosine and sine, you just have cosine, but you have another constant right here called the phase angle. So the reason you can do it that way is when you add a cosine and a sine, when you add two trigonometric functions of the same frequency, you can write it as just one trigonometric function with the phase shift. Getting a little off topic though. So x is a times cosine of a constant times t. Now that constant, it has to be whatever value it needs to be, so that when you take two derivatives, you get a k over m in addition to that minus sign. Okay, so from the chain rule, you're gonna get this constant come out 2 times for each of the two derivatives. So that constant needs to be so that when you have it appear twice right here. So let me do this. Let's just call it omega right now. This W-looking thing. If we take one derivative, so dx dt is, so remember derivative of cosine is minus sine, so we have minus a sine omega t, but then from the chain rule we have to have the derivative of the inside. So this w, this omega, appears again. And then the acceleration is the derivative of velocity with respect to time. And then from the chain rule this comes out another time. So this is minus a omega squared cosine omega t. So this is, if we compare, if knowing that x is a cosine omega t, this is minus omega squared times x. So a, or two derivatives of x, is minus omega squared times x, and that has to equal this. So this tells us what omega needs to be. So that thing that's multiplying the x inside the cosine has to be squared at k over m times 10. So what this equation is saying is that this mass is going to oscillate back and forth, just like a cosine function oscillates back and forth. Okay, so this is describing the x position of the mass as a function of time. So you start out at a, you go through the equilibrium position, and then you go to minus a, and then 0, and then a, 0, minus a. So this mass is bouncing back and forth between its two extremes. So if you stretch the spring's going to pull back on the mass overshoots the center, so it's moving to the left, and it goes past where it wants to be. So what I mean by that is that the mass actually has no net force right here, but if it was accelerating the whole time before that to the left, then it's moving to the left. So even though there's no net force, that just means the velocity is not going to change. So it moves right through the equilibrium position, and it starts to compress the spring, and the spring doesn't like that, and it pushes back to the right, slowing it down again. So this mass is oscillating back and forth between x equals positive a, and x equals minus a. So your book is motivating. So first it just says k and m are 1, and see how two derivatives of a cosine gives you minus itself again. And then it goes back and says, oh, by the way, that if those weren't equal to 1, then this is what it has to be, the k and the m. Yeah. Okay, so the point of this story is, you're gonna need this formula. The point of the story is that the motion. So this is called simple harmonic motion, which we'll come back to later in the course, but we might use the term simple harmonic motion. Hooke's law. The dynamics of Hooke's law is simple harmonic motion, which means that the motion is oscillatory, right? Sinusoidal. If you have a mass bouncing on a spring like this, it looks like a sine or a cosine. The position as a function of time looks like a sine or a cosine. Okay, I think we can go back to our problem here. A mass stretches a spring by 2 centimeters. The spring has spring constant k equals 450 newtons per meter. A, what is the initial force on the mass from the spring? Well, this might just be a straightforward application of Hooke's law. So our problem so we have our picture in mind. The spring is stretched out from equilibrium. So from equilibrium, it's stretched out 3 centimeters. Was it 3 centimeters? No, 2 centimeters. Sorry. 2 centimeters. And this is, m is half a kilogram. Notice the problem didn't ask for a picture, but it helps visualize what's going on, right? And then k, the spring constant for the spring, is 450 newtons per meter. It's a sign of how stiff that spring is. Okay, A, Hooke's law. F spring is minus kx is minus 450 newtons per meter. And then x is 2 centimeters, but we want the meters to cancel out. Or in other words, we should probably just plug everything in SI units so that we get the SI units of force. So we have to put 0.020 meters. Okay, so divide by 100 and multiply by 2. So take this, divide by 100, multiply by 2, you get 9. So this is negative 9 newtons. So the negative means that, our positive x direction is defined to be the direction that we stretch the spring. The negative means that the direction of the force on the mass is in the direction that is opposite that. Okay, so not the direction that stretches the spring out, but the direction that compresses the spring. So the spring is pulling back on the mass, back inwards towards x equals 0, towards our equilibrium position. Okay, so the minus sign means inwards. So spring pulls mass back inwards. So not the direction where it's stretching out, but back in. Okay, and then the next question, how much time does it take for the mass to first come to rest? So this involves understanding the solution a little bit, this a cosine squared of k over m. All right, now this mass is going to go from 2 to 0 and then to minus 2. Okay, so x equals plus 2 centimeters and then x equals minus 2 centimeters. So the first moment it comes to rest is when it goes to minus 2 centimeters. The mass is going to move to the left, actually increase in speed until it passes the equilibrium position, then decrease in speed until it comes to -2. And that's momentarily at rest, and then the compressed spring is going to push it to the right again. Well, it's always pushing it to the right, but when the moment it stops, it's going to start it moving to the right as well. So what will help us here is knowing our equation. X is a function of time, is a cosine square root of k over mt. Remember, we can use just the cosine and we don't need the sine piece as long as we start out with the mass at x equals positive a. Right? When we plug in t equals 0, we get x equals a, which is the case here. So that's perfect. We can use this. Our equation is going to be 2 centimeters cosine. Now square root of k over m, let's see what that is. Square root of k over m is square root of 450 newtons per meter divided by the mass is half a kilogram. So as long as k is in SI units, which is newtons per meter, and m is in SI units, then this is going to be a 1 over time. Now how do I know that? Well, just from dimensional analysis. Look at the square root of k over m times t. Anything inside a cosine has to be dimensionless. So these two things have to multiply to give no dimensions, or no units, which means if we have seconds right here, this has to be 1 over seconds. Okay, so 450 over a half is 450 times 2 is 900. Square root of 900 is 30. This is 30. Inverse seconds, so 1 over seconds are the units here. 30 per second. You might see this written as 30 radians per second. A radian is unitless. Okay, the nice thing about radians is that it's sort of the most natural unit. So you might see radians per second, you might just see 1 over seconds. So let's do 30, this is 30 radians per second times t. Right? So this is x at all times. Now we want to find the time where this thing is at rest. And it's at rest when x equals -2 centimeters. So I'm going to plug in x, let's call it t stop. This is when it first comes to stop, to rest. This is going to be -2 centimeters. So we're plugging in, maybe I should scoot this over. X at t stop is -2 centimeters is equal to, so we were just plugging in for x at that. So I have in mind like this. We're plugging in for x is -2 centimeters, and now we're just copying down the right-hand side. This is 2 centimeters cosine. So I'm just copying everything down, except this is a special value of t. So this is t stop. This equation is true for all t. This t is the particular value of time, so that x equals -2 centimeters. So notice how we're plugging in a particular value of x on the left-hand side. That particular value of x comes with a particular value of t. Okay. So we have -2 centimeters, 2 centimeters, dividing both sides by 2 centimeters, we get -1 is cosine 30. And on purpose, I'm sometimes writing radians, sometimes not, because you'll see both ways. So cosine of something has to equal -1. What does that something have to be? Well, so a cosine graph looks like this. It starts out at 1. This is cosine of whatever's on the inside. Let's just call it z. Cosine of z versus z. When does it first equal -1? Well, you may remember that cosine takes, it's 2 pi. The period is 2 pi. So when z is 2 pi, that's it. Cosine of 2 pi is 1 again. But halfway, when that argument is pi, that's when you get -1. Cosine of pi is -1. So this is equal to pi. That's the first time that this thing comes to rest. Okay, so setting these two equal to each other, you get t stop is pi over 30 seconds. the 30 times 1 over seconds, let me actually write it this way, pi over 31 over seconds. But then the 1 over seconds on the denominator just becomes seconds on the numerator. So this is pi over 30 seconds. Right, so this is approximately 0.10 seconds, 10 milliseconds. So it only takes 1/10 of a second for this for this mass to go to the left and then momentarily come to rest. So it's oscillating pretty quickly. Right? Twice this time it would come back to its original position. Okay, so we'll do more algebra with simple harmonic motion towards the end of the course, but this is what we want you to know throughout the course in order to analyze springs in problems. Right? So this will be good for now. Okay.